So what do the fuller examples look like in this section? We'll just need one. It's kind of a shorter section. Example, let's take a look at r equals 5 over 3 minus 2 sine theta. In part A, we're going to be asked to find the eccentricity and identify the conic, kind of like what we were doing just a moment ago. Well, all right, to identify or to find the eccentricity, we'll do that first. We need it to fit one of those forms for a polar conic, right? What does that mean? Well, we've done this sort of thing a few times in the course already. We need to make this look like that fit. What does that mean? We really want a 1 right there. If we can get a 1, then we can find E, we can find D, and we can go about it. So if we see a 3, let's divide everything by 3. And here we go. R equals 5 over 3 all over 1 minus 2/3 sine theta. Hey, all right. Well, I can find the eccentricity right here. Remember, it's always the absolute value of that number. So I'm going to think of E as equaling negative 2/3. So the eccentricity, I take the absolute value, is positive 2/3. Now it's important to recognize E as negative 2/3 for when we have to find the directrix, the value of D. We take the absolute value of that. That's the eccentricity. And well, we got a number less than 1, so we know that that is an ellipse. Let's move on to part B. And well, when you know it, what is the equation of the directrix? Okay, here we need the D. Well, if E is negative 2/3 and we have a 5/3 on top, we know that E times D equals 5/3. So negative 2/3 times D equals 5/3. And well, D equals negative 5 over 2. That will get us the equation of the directrix. Of course, we have to figure out, should it be x equals or should it be y equals? But we can go back and see, it was a sine, so that means it's an ellipse, but it's more elongated vertically, so its directrix is down here. It's a horizontal line, so we get the horizontal line, y equals negative 5 over 2. We just take that number for whatever it is. And in part C, this is kind of cool. What is the polar equation if we rotate this ellipse by an angle of pi over 4? Now, what I'll invite you to do, go and at this point even go back and graph in Desmos. And you could graph even the original form in Desmos. And why not graph that directrix as well? And think, hey, if we were going to rotate this by an angle of pi over 4, so the focus is going to stay at the origin, but it's going to rotate counterclockwise by pi over 4. What would the equation be? Okay, so it sounds very, very complicated, but it turns out if you're working in polar is built to make rotations. This is going to be the easiest thing ever. All you got to do is exchange theta for theta minus pi over 4. We're doing a shift, right? So in the Cartesian coordinate system, when you do a shift, you do something like x minus h, right? And it shifts it to the right by that many units. Well, if you're doing polar, if you want to rotate, a shift is a rotation in polar. So exchange your theta for theta minus however far you want to rotate. Hey, graph this in Desmos as well, and you'll see them next to each other, and you'll just see that rotation by, what is that, 45 degrees. So most of the questions you're going to see are this style. There's a couple at the end that are application based. We're just going to do one quickly here. So this theorem says an ellipse with one focus at the origin has the polar equation r equals a times 1 minus e squared all over 1 plus e cosine theta. A different way to think about the numerator here, instead of e times d, if you have an ellipse, you can think of it like this, where a is the semi-major axis. So I don't think I didn't mention that. Maybe you remember this back from pre-calc. So in an ellipse, we think of the longer axis going through the center as the major axis. The semi-major axis, half of that is A. So that's how we think of A, but that's the semi-major axis. Or if it was faced vertically, then again the major axis goes the long direction, so the semi-major axis, would be like that. Okay, anyway, this is the cosine version, so it's this direction. That length A we can plug in. Okay, so the question is, Jupiter has an orbit with E equals 0.048, very small eccentricity, almost circular, and it has an A equal to 1.56 times 10 to the 9th kilometers. So if you found the center of Jupiter's orbit and you thought of, okay, so then when's the furthest that Jupiter is from that center? That's your semi-major axis. Well, an equation for its orbit, no problem. I know E, I know A, it's an ellipse. I'm just going to plug it all in there, and we got it. R equals 1.56 times 10 to the 9th. Quantity 1 minus E squared. I'm just going to put it in like that. All over 1 plus E cosine theta. There's the equation for Jupiter's orbit in polar coordinates. Pretty cool. That is our last example. That is the end of our final chapter. Go check out the homework. See you guys in the live meeting.